You clicked the right video. Earth's movement through space isn't as simple as just spinning and orbiting. It's a breathtaking cosmic journey shaped by powerful forces that influence everything from our days and seasons to the distant future of our planet. Right now you're moving at unimaginable speeds, faster than a bullet, faster than a rocket, yet you don't feel a thing. The world around you seems motionless, but in reality Earth is spiraling, tilting, wobbling, and being pulled by immense cosmic forces on a journey through the vastness of space. How fast is Earth truly moving? What unseen forces shape our journey through the universe? Does Earth travel in a straight line, or is our path far more chaotic than we realize? And what does this motion mean for the future of our planet? Earth feels solid beneath our feet, but we are constantly in motion, traveling through space in multiple ways at the same time. Most people are familiar with two basic motions, rotation and orbit, but Earth's movement is far more complex than that. We're not just spinning and orbiting, we're spiraling, wobbling, tilting, and being pulled by immense gravitational forces on a journey that never stops. Every day, Earth completes a full rotation on its axis. Earth's rotation is the reason we experience day and night. It means that our planet is constantly spinning around an invisible line called the axis, which runs from the North Pole to the South Pole. Earth completes one full spin approximately every 24 hours. This rotation is why the sun appears to rise in the east and set in the west each day, even though it's actually Earth that is moving. Even though we don't feel it, Earth is moving very fast. At the equator, the surface is spinning at about 1,670 kilometers per hour, which is faster than the speed of sound. However, if you are closer to the North or South Pole, you're moving slower because the circumference of the Earth is smaller there. We don't feel this motion because of inertia, which means that everything around us, including the air, land, and oceans, is moving at the same constant speed. It's similar to when you're on a smoothly moving train or airplane. You don't feel the motion unless it speeds up, slows down, or changes direction. As Earth spins, different parts of the planet face the sun at different times. The side that faces the sun experiences daylight, while the opposite side is in darkness, experiencing night. As Earth continues to rotate, the sun appears to move across the sky until it sets, and night begins. This continuous motion creates the cycle of morning, afternoon, evening, and night. Earth's rotation is not perfectly stable. It has a slight wobble due to the gravitational pull of the moon and the sun. One type of wobble, called precession, occurs over a cycle of about 26,000 years. This means that over thousands of years, the North Pole does not always point at the same star. Another type of wobble, called nutation, happens over shorter periods, about 18.6 years, slightly shifting Earth's tilt back and forth. Earth's rotation is also gradually slowing down. The reason for this is the moon. The moon's gravity pulls on Earth's oceans, creating tides. These tides act as a kind of braking force, slowing down the planet's spin little by little. This effect is very small, adding only about 1.7 milliseconds to the length of a day every century. But over millions and billions of years, this adds up. About 1 billion years ago, a day on Earth was only about 18 hours long. In the far future, days will be much longer than 24 hours. The slowing of Earth's rotation also affects the moon. As Earth loses rotational speed, the moon is slowly moving farther away from us at a rate of about 3.8 centimeters per year. This means that in the distant future, the moon will appear smaller in the sky than it does today. Earth's rotation also affects the way air and ocean currents move. Because the planet is spinning, winds and ocean currents don't travel in straight lines. Instead, they curve due to an effect called the Coriolis effect. This is why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Although we don't feel Earth's movement, everything we experience, sunrises, sunsets, the passage of time, changing weather patterns, is influenced by our planet's constant spinning. It is a motion that has continued for billions of years and will continue to shape our world far into the future. Earth's orbit around the sun is another motion we take for granted. Earth's orbit around the sun is the reason we have years and seasons. Instead of staying in one place, Earth is constantly moving through space, following a path around the sun. This journey takes about 365.25 days to complete, which is why we have leap years every 4 years to make up for the extra quarter of a day. Earth does not move in a perfect circle around the sun. but follows an elliptical or slightly oval-shaped path. This means that our distance from the Sun changes throughout the year. At its closest point, called perihelion, Earth is about 147 million kilometers away from the Sun. At its farthest point, called aphelion, it is about 152 million kilometers away. The difference in distance does not cause the seasons, as some might think. Instead, seasons are caused by Earth's tilt on its axis. Earth is tilted at an angle of about 23.5 degrees. This tilt remains fixed as Earth orbits, meaning that different parts of the planet receive different amounts of sunlight at different times of the year. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere tilts away and experiences winter. 6 months later, the situation is reversed, with the northern hemisphere in winter and the southern hemisphere in summer. The tilt also affects the length of daylight hours, making summer days longer and winter days shorter. Earth moves around the Sun at an average speed of about 107,000 kilometers per hour. Even though this speed is incredibly fast, we don't feel the motion because everything around us, including the atmosphere, is moving along with us. Earth's orbit is also affected by gravitational forces from other planets, particularly Jupiter and Saturn. These massive planets slightly tug on Earth as it moves, causing small changes in the shape of our orbit over long periods of time. Over thousands of years, Earth's orbit shifts between being more circular and more elliptical, a cycle that can influence climate patterns on a long time scale. Another effect of Earth's orbit is precession, which is a slow wobble in the direction of Earth's axis. This happens because the gravitational pull of the Sun and Moon causes Earth's axis to move slightly over time, completing one full cycle approximately every 26,000 years. Because of this, the North Star won't always be the same. It changes over thousands of years. As Earth moves in its orbit, it also drags the Moon along with it. The Moon orbits Earth, but together Earth and the Moon travel around the Sun as a system. The Sun's gravity keeps Earth in its orbit, preventing it from flying off into space. At the same time, Earth's motion around the Sun counteracts the pull of gravity, creating a stable balance that keeps us on our yearly path. Our planet has followed this same orbital pattern for billions of years, but it is not permanent. Over extremely long timescales, changes in gravitational influences, the Sun's energy output, and even interactions with passing stars could alter Earth's orbit. However, these changes happen so slowly that they won't affect life in any noticeable way for millions of years. Even though we don't feel it, Earth's orbit is a continuous journey through space, shaping the flow of time, the change of seasons, and the conditions that make life possible. As Earth orbits the Sun, we might imagine the solar system as a collection of planets simply circling in place. But in reality, the entire solar system is moving through the Milky Way galaxy, and it's not moving in a straight line. The Sun, along with all the planets, moons, and other objects in the solar system, is traveling through space as it orbits the center of the Milky Way galaxy. This journey takes an enormous amount of time, around 225 to 250 million years, to complete just one orbit. The last time our solar system was in this same position in the galaxy, dinosaurs were just beginning to walk the Earth. The solar system moves at an average speed of about 828,000 kilometers per hour, but because space is so vast, we don't notice this motion in our daily lives. If we could see the galaxy from far away, we would notice that our solar system is not following a simple circular path. Instead, it moves in a slightly wavy pattern as it orbits, bobbing up and down through the plane of the Milky Way like a boat riding waves on the ocean. This motion happens because the gravity of nearby stars and other galactic structures pulls on our solar system, slightly altering its path over time. The Milky Way itself is a massive spiral galaxy made up of billions of stars, including our Sun. Our solar system is located in one of the outer spiral arms called the Orion Arm, about 27,000 light-years away from the galaxy's center. In the middle of the Milky Way, there is a supermassive black hole known as Sagittarius A*, which is millions of times more massive than our Sun. The gravity of this black hole, combined with the gravitational pull of the entire galaxy, is what keeps our solar system in its orbit. As the solar system moves through the galaxy, it also encounters different regions of space. Some areas are relatively empty while others are filled with cosmic dust, gas, and radiation. These interstellar environments can have subtle effects on the solar system, potentially influencing things like the movement of comets and the amount of cosmic rays that reach Earth. Scientists believe that passing through dense cosmic clouds or high-energy regions of the galaxy might even affect Earth's climate over long periods of time. The motion of the solar system is not completely stable. Over millions of years, its orbit can be influenced by passing stars or other gravitational forces. If a nearby star were to come close to our solar system, it could disturb the Oort cloud, a distant region filled with icy comets. This could send some of these comets hurtling toward the inner solar system, increasing the likelihood of impacts on Earth and other planets. The future of our solar system's journey through the galaxy is also shaped by the movement of the Milky Way itself. The entire galaxy is traveling through space at about 2.1 million kilometers per hour, moving toward a giant cosmic structure called the Virgo supercluster. Even more dramatically, the Milky Way is on a collision course with the Andromeda galaxy, which is the closest large galaxy to our own. Andromeda is approaching us at a speed of about 402,000 kilometers per hour. In about 4.5 billion years, the two galaxies will merge, creating a completely new galactic structure. This event won't destroy our solar system, but it will completely reshape the night sky and the cosmic neighborhood we live in. Even though we don't feel any of this motion, the reality is that everything around us is constantly moving at incomprehensible speeds. Earth is orbiting the sun is orbiting the galaxy is moving through the universe, and all of this is happening at the same time. Our place in the cosmos is never the same, and the journey of the solar system through the Milky Way is a process that has been unfolding for billions of years and will continue for billions more. Earth isn't just spinning, orbiting the sun and moving through the galaxy. The Milky Way itself is also traveling through space at 2.1 million kilometers per hour. The entire galaxy, including billions of stars, planets, and clouds of gas and dust, is in motion, following a complex journey through the cosmos. Our solar system, which is just one small part of the Milky Way, is carried along with it. Even though we don't feel this movement, everything in the galaxy is shifting and changing over time. The Milky Way is a spiral galaxy, meaning it has a central bulge surrounded by vast, curving arms that stretch outward. The entire structure rotates around its center, which contains a supermassive black hole called Sagittarius A*. This black hole is millions of times the mass of the Sun, and its intense gravitational pull helps keep the galaxy together. The stars in the Milky Way orbit this central point, with those closer to the center moving faster than those farther away. The Milky Way is not just spinning, it is also traveling through space. The entire galaxy is moving at an incredible speed of about 2.1 million kilometers per hour. It is part of a larger group of galaxies called the Local Group, which includes Andromeda, the Triangulum Galaxy, and many smaller galaxies. One of the most dramatic aspects of the Milky Way's motion is its future collision with the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will collide and merge into a single, much larger galaxy. This event will completely reshape the Milky Way, altering the positions of stars and potentially forming new regions of intense star formation. Despite this massive collision, individual stars and planets are unlikely to crash into each other because of the vast distances between them. Instead, gravity will slowly pull the two galaxies together, blending their stars and reshaping their structures. The movement of the Milky Way affects everything within it. As it travels through intergalactic space, it encounters cosmic clouds of gas, radiation, and other galaxies. These interactions can influence the formation of stars, the structure of the galaxy's arms, and even the environment of our solar system. Some scientists believe that as the Milky Way moves, it may pass through regions of space that expose Earth to more cosmic radiation, which could have long-term effects on climate and biological evolution. The galaxy's motion is also influenced by dark matter, an invisible substance that makes up most of the universe's mass. Dark matter does not emit light or energy, so we cannot see it directly, but its gravitational effects can be observed. The Milky Way appears to be surrounded by a vast halo of dark matter which helps shape its motion and structure. This unseen force plays a major role in how galaxies form and move through space. The movement of the Milky Way is part of the larger story of the expanding universe. Ever since the Big Bang, galaxies have been drifting apart, stretching the fabric of space itself. However, while the universe as a whole is expanding, local gravitational forces, like those between the Milky Way and Andromeda, can overcome this expansion and bring galaxies together. The Milky Way is part of the local group. The local group is not a fixed structure in space. It is a collection of galaxies that are moving together under the influence of gravity. The local group is about 10 million light-years across and contains around 80 galaxies, including the Milky Way, Andromeda, the Triangulum galaxy, and many smaller dwarf galaxies. Each galaxy within the local group is moving in its own way, but the entire group also moves as a whole through the vastness of space. Andromeda is the largest galaxy in the local group. Apart from the Milky Way and Andromeda, the other galaxies in the local group also move around in different ways. Some of the smaller dwarf galaxies, such as the Magellanic Clouds, are orbiting the Milky Way. Others, like the Triangulum galaxy, are possibly orbiting Andromeda, or may eventually be pulled into the future Milky Way-Andromeda merger. Some dwarf galaxies are moving chaotically as they are tugged by the gravity of their larger neighbors, and some may eventually be absorbed by the Milky Way or Andromeda. The entire local group itself is moving as a whole through the universe. It is traveling toward the Virgo cluster, which is the center of the larger Virgo supercluster, a collection of thousands of galaxies. This motion is happening at a speed of about 1.2 million kilometers per hour. The gravity of the Virgo cluster is pulling the local group and other nearby galaxies toward it, slowly reshaping their positions over time. The local group's motion is part of the grand structure of the cosmos. It is not moving in a straight line, but rather following a complex path influenced by the pull of different cosmic forces. Over billions of years, the local group's movement will change, and its galaxies may shift, merge, or even be absorbed into larger galactic structures. The universe is not static. Everything is constantly in motion, and the local group is just one small part of the endless journey of galaxies across the cosmos. The Virgo supercluster is a vast collection of galaxy groups and clusters that spans about 110 million light-years across. It contains thousands of galaxies, including our own local group. But like everything in the universe, the Virgo supercluster itself is not stationary. It is moving through space, influenced by even larger cosmic structures. The entire Virgo supercluster is moving toward a massive gravitational force known as the Great Attractor, which is located about 250 million light-years away. This movement happens at an incredible speed of about 2.1 million kilometers per hour. The Great Attractor is a dense region of space filled with galaxies, dark matter, and possibly even unknown cosmic structures that exert a powerful gravitational pull on everything around it. Scientists believe this is one of the strongest gravitational influences in our region of the universe, and it is slowly drawing the Virgo supercluster, along with thousands of other galaxies, toward it. Even though these movements happen at mind-boggling speeds, they occur over incredibly long timescales. It will take billions of years for the Virgo supercluster to reach the Great Attractor, and by then the universe itself will have changed significantly due to its ongoing expansion. Galaxies will continue to merge, new stars will form, and the cosmic structures that shape the Virgo supercluster's motion today may look completely different in the distant future. The Great Attractor is a massive gravitational anomaly in space in the direction of the Centaurus constellation. It is pulling entire galaxy clusters toward it, including the Virgo supercluster, which contains our Milky Way and thousands of other galaxies. However, the Great Attractor itself is not stationary. It is also moving through space, influenced by even larger cosmic structures. The movement of the Great Attractor happens because of the enormous gravitational forces at play. Instead of a single object, the Great Attractor is a dense region made up of galaxy clusters, dark matter, and other unknown cosmic structures. Its gravitational pull is strong enough to influence the movement of entire superclusters, but it is not the final destination in this cosmic flow. Because of the ongoing expansion of the universe, the overall movement of galaxies and clusters is complex, while space itself is stretching due to cosmic expansion. Local gravity is strong enough to pull galaxies together in certain regions. This is why galaxies within superclusters are moving toward each other instead of simply drifting apart. The Great Attractor, the Virgo supercluster, and even the local group are all following this gravitational flow, moving toward the denser, more massive regions of the universe. The full nature of the Great Attractor is still not completely understood. It lies in an area of space called the zone of avoidance, where dust and stars from our own Milky Way block much of our view, making it difficult for telescopes to study in detail. However, scientists have been able to use infrared telescopes and radio waves to peer through this obstruction and get a better understanding of the vast structures pulling galaxies toward this region. Scientists have discovered that the Great Attractor is part of an even larger supercluster called the Laniakea supercluster, which contains over 100,000 galaxies. The entire Laniakea supercluster, including the Great Attractor, is moving toward an even more massive region of space known as the Shapley supercluster, which is the largest known concentration of galaxies in our nearby universe. Even though we don't feel it, our entire galaxy, along with thousands of others, is being pulled by this massive structure as part of the grand cosmic motion that shapes the universe. Everything we know, from the smallest planets to the largest galaxy clusters, is part of this vast and endless journey through space. The Shapley supercluster is one of the most massive and densest known superclusters in the universe. It lies about 650 million light-years away and contains over 8,000 galaxies, forming a giant gravitational structure that is pulling entire clusters, including the Laniakea supercluster, which contains the Milky Way, toward it. This immense collection of galaxies, dark matter, and other cosmic structures creates one of the most powerful gravitational centers in the observable universe. However, just like everything else in space, the Shapley supercluster itself is also moving. The movement of the Shapley supercluster is influenced by an even larger gravitational force. Scientists have discovered that Shapley is not the final destination of our cosmic journey. It is being pulled toward an even greater structure called the dipole repeller, and possibly toward another massive concentration of galaxies known as the Sloan Great Wall. These structures, which lie even farther away, are shaping the large-scale motion of galaxy clusters across hundreds of millions of light-years. At the same time, the Shapley supercluster is also part of the large-scale motion of the universe itself. The expansion of the universe, caused by dark energy, is stretching space over time, causing most galaxies and galaxy clusters to move away from each other. However, within localized regions where gravity is strong, such as Shapley, galaxies continue to move toward one another instead of simply drifting apart. This creates a complex web of movements where different parts of the universe are expanding while large superclusters are still coming together due to their immense gravitational pull. The exact motion of the Shapley supercluster is still being studied, but it is clear that it is one of the largest influences on the motion of galaxies in our region of the universe. The Milky Way, Andromeda, the Virgo supercluster, and even the Great Attractor are all part of this larger cosmic flow, being slowly drawn toward Shapley over billions of years. In the far future, Shapley may merge with other superclusters to form an even more massive structure, reshaping the large-scale arrangement of galaxies. However, because these movements happen on timescales of billions of years, the universe as we know it will continue evolving in ways that are difficult to predict. What is certain is that the Shapley supercluster plays a major role in the movement of galaxies across vast distances, and our Milky Way is just one small part of this grand cosmic journey. The dipole repeller is a vast region of space that appears to be pushing galaxies away from it. Unlike structures such as the Great Attractor or the Shapley supercluster, which pull galaxies toward them with their immense gravity, the dipole repeller is an underdense region, a cosmic void with very few galaxies and very little matter. Because of this, it has a weaker gravitational pull than the denser regions of space, and as a result, surrounding galaxies appear to be moving away from it. The movement of the dipole repeller itself is tied to the large-scale structure of the universe. It does not move in the way a galaxy or a supercluster does because it is not a physical object, but rather a region of lower density in the cosmic web. However, the forces that shape the universe are constantly evolving, meaning that even cosmic voids like the dipole repeller can shift and change over billions of years as matter gets redistributed. The dipole repeller plays a key role in the motion of our local group, the Virgo supercluster, and even the Shapley supercluster. It works together with the gravitational pull of massive structures like Shapley and the Great Attractor to create a large-scale flow of galaxies. Essentially, galaxies in our region of the universe are being pulled toward the Shapley supercluster, while simultaneously being pushed away from the dipole repeller. This creates a stream-like motion of galaxies, shaping the structure of the cosmos. Scientists discovered the dipole repeller by studying the movement of galaxies across hundreds of millions of light years. By analyzing how galaxies shift and flow in space, they realized that something was pushing them from one direction, while something else was pulling them from another. This helped reveal the presence of the dipole repeller and its role in the grand movement of the universe. Even though it lacks a strong gravitational center, the dipole repeller is part of the ever-changing cosmic landscape. As galaxies continue to move and evolve, voids like the dipole repeller may change in shape, size, and influence over billions of years. The universe is not static. It is always shifting, expanding, and reshaping itself, and the dipole repeller is just one piece of the enormous puzzle that governs the motion of galaxies on a cosmic scale. The universe moves in several ways, but not like a planet or a galaxy moving through space. The most fundamental motion of the universe is its expansion. Since the Big Bang, space itself has been stretching, causing galaxies to move away from each other. This does not mean galaxies are traveling through space like a car on a highway. Instead, space itself is growing, carrying galaxies along with it. The farther apart two galaxies are, the faster they move away from each other. This discovery, made by Edwin Hubble in the 1920s, showed that the universe is continuously expanding, and this expansion is happening everywhere, even though we cannot feel it. This gives Earth an extra direction and speed we don't normally think about. The universe's expansion is not slowing down, it is actually speeding up. Scientists believe this acceleration is caused by a mysterious force called dark energy. Dark energy makes up about 68% of the universe and seems to be pushing space outward, making galaxies move apart faster than they normally would. If this acceleration continues forever, galaxies will become so far apart that they will no longer interact with each other. The universe is structured like a giant cosmic web, made up of galaxies, dark matter, and massive voids. This cosmic web is constantly shifting over billions of years. The movement of galaxies within this web is influenced by the unseen presence of dark matter, which does not emit light, but provides the extra gravity that helps shape the universe's structure. One interesting discovery is that our entire local group of galaxies is moving at about 630 kilometers per second relative to the cosmic microwave background, which is the leftover radiation from the Big Bang. This means that on a large scale, everything in our region of space has a collective motion in one direction. This motion is likely caused by the gravitational pull of large-scale structures such as the Shapley supercluster and the dipole repeller, which push and pull galaxies across the universe. The motion of the universe also depends on its future. If dark energy continues to push space outward, the universe will keep expanding indefinitely, causing galaxies to drift apart until they are isolated in empty space. If gravity eventually overcomes dark energy, the universe could slow down, stop expanding, or even collapse in what is called the Big Crunch, reversing the expansion and bringing everything back together. Scientists are still studying which of these possibilities is most likely. The universe is not moving through anything because it is everything. There is nothing outside of it for it to move through. Instead of traveling through space, the universe is space itself, and space is stretching and expanding over time. This cosmic motion has been happening for 13.8 billion years and will continue shaping the universe for billions of years to come. Even though we don't feel it, we are constantly in motion, shaped by forces beyond our control. And with every second that passes, we continue this journey through the cosmos, one that began billions of years ago and will continue for billions more. In summary, Earth not only rotates on its axis and orbits the Sun, but it also moves through space in a much more intricate way. The Sun, along with the entire solar system, travels around the center of the Milky Way within the Orion arm. The Milky Way itself is part of the Local Group, a gravitationally bound collection of galaxies. The Local Group is moving toward the Virgo cluster, though it is not inside it. Both belong to the larger Laniakea supercluster. This supercluster is being drawn toward the Great Attractor, a powerful gravitational anomaly. The Great Attractor is part of the Shapley supercluster, one of the most massive known galaxy concentrations. Additionally, the Shapley supercluster and nearby structures are influenced by the dipole repeller, a low-density region that appears to push galaxies away. Positioned opposite the Great Attractor, the dipole repeller contributes to large-scale cosmic flows. Beyond these local motions, the entire universe is expanding due to dark energy, causing distant galaxies to recede from one another over time. Earth's movement through space is far more complex than simple rotation and orbiting the Sun, as it is part of a vast and dynamic cosmic dance. The universe expansion adds a kind of invisible motion, gently pulling Earth along with the rest of the universe as it grows bigger and bigger. Which of Earth's motions surprised you the most? Do you think these movements could have effects we don't yet understand? Let us know your thoughts in the comments. Disclaimer: as an Amazon and other affiliate, I earn from qualifying purchases at no additional cost to you. Do you like the video and want to make videos like this? Turn text into stunning videos in seconds. Get free trial and unlock your creative potential. You can create even better videos than mine. No editor is required. Check out the link in the video description below. Thank you for joining us on this journey through space. What topic should we explore next? Drop your ideas in the comments. Your suggestion might be in our next video. Please like and share the video, and please do not forget to subscribe for more videos.